This is the first image ever taken of a black hole. It was captured in 2019 by a network of 8 telescopes spread across the planet, linked together to form a virtual dish the size of the Earth. The black hole sits at the center of a galaxy called Messier 87, 55 million light-years away, and it weighs 6.5 billion times more than our Sun. And this is the second black hole ever photographed, Sagittarius A star, the one at the center of our own Milky Way. And despite being more than 1,000 times smaller than the first, it looks almost identical. That was strange, because when scientists looked deeper at the way the light was behaving, they found something no one expected. Strong, organized magnetic fields spiraling from the very edge of the event horizon. A structure so similar between two completely different black holes that it hinted a clue to something even bigger, a hidden jet of matter being launched at nearly the speed of light from the heart of our own galaxy. So what has NASA actually found inside a black hole? To understand what scientists actually found, you need to know one thing about light. It oscillates, and sometimes that oscillation has a preferred direction. When it does, we call the light polarized. You have encountered polarized light before. It bounces off roads, water, glass. Your sunglasses filter it. But to human eyes, polarized light looks identical to normal light. You cannot tell the difference without instruments. Now, here is where it gets interesting. In the superheated plasma swirling around a black hole, charged particles spiral along magnetic field lines. As they do, they imprint a polarization pattern on the light they emit, a pattern that runs perpendicular to the magnetic field. If you can measure that polarization, you can effectively map the magnetic field structure around a black hole. You can see something invisible. And that is exactly what the Event Horizon Telescope collaboration did next. Imaging Sagittarius A star in polarized light was not easy. This black hole does not sit still for pictures. Its environment is highly dynamic, swirling and flickering on timescales of minutes. The first image, released in 2022, was itself an average of multiple exposures stitched together to account for the constant motion. Some theoretical models predicted magnetic fields so scrambled and turbulent that constructing a polarized image would be impossible. But nature was not so cruel. In 2024, the collaboration released a new image. Not in ordinary light, in polarized light. And for the first time, astronomers could see the magnetic fields spiraling from the edge of our galaxy's central black hole. The fields were strong, they were twisted, and they were highly organized. Sarah Isaun, a NASA Einstein Fellow at the Center for Astrophysics at Harvard, described the finding. The team found strong, twisted, and organized magnetic fields near the black hole at the center of the Milky Way. And those fields had a strikingly similar polarization structure to what had been observed in the much larger and more powerful M87 star black hole. That similarity was not expected. M87 star is pulling in matter at a much faster rate. Its environment is completely different. Its mass dwarfs Sagittarius A star by a factor of more than 1,000. Some researchers expected the magnetic fields to look entirely different, but they turned out to be almost the same. And that raises a very big question. If two black holes this different share the same magnetic architecture, is it possible that this structure is not special to them? That it is a universal feature of all supermassive black holes, regardless of mass, size, or galaxy? Angelo Ricart, a Harvard Black Hole Initiative Fellow, put it this way: polarized light teaches us a lot more about the astrophysics, the properties of the gas, and the mechanisms that take place as a black hole feeds. This was not just a prettier picture. It was a fundamentally new kind of information. But the magnetic fields were not just interesting on their own. They pointed to something else, something that nobody has been able to find yet. Previous studies of M87 star had revealed that the magnetic fields around that black hole were powerful enough to launch jets. These are enormous beams of ionized matter, accelerated to nearly the speed of light, shooting outward from the poles of the black hole. Some jet beams extend for millions of light years. In the case of M87 star, the jet is dramatic and unmistakable. Material falling onto the black hole gets redirected into a tightly focused stream of particles, powerful enough to be referred to as relativistic jets. We have seen this jet. We have photographed it. It is real, but in Sagittarius A star, no jet has ever been observed. The polarized light data, however, hints that one may be hiding. The magnetic field structure around our galaxy's central black hole is strikingly similar to the structure that powers the jet in M87 star. Some researchers believe that Sagittarius A star may indeed be launching a jet, one that is simply too faint or too obscured for us to see with current instruments. Maria Felicia de Laurentiis, the EHT deputy project scientist, noted that with a sample of two black holes with very different masses and very different host galaxies, it is important to determine what they agree and disagree on. Since both are pointing towards strong magnetic fields, it suggests that this may be a universal and perhaps fundamental feature of these kinds of systems. Think about what that would mean. If every supermassive black hole, no matter how quiet it appears from the outside, is secretly driving enormous outflows of energy into the cosmos. The EHT has been adding new telescopes to its network since 2017, including the Greenland telescope and instruments on Kitt Peak. Each year, the images get sharper, and each year, the chance of finding that hidden jet grows. So we have mapped the edges. We have traced the magnetic fields. We have seen the shadow. But there is a question that has haunted physicists and the public alike for as long as black holes have been understood. What actually happens if you fall into one? Let us say you get too close. You cross the innermost stable circular orbit, the boundary beyond which no stable orbit is possible. Once you cross it, you start drifting inward, and you are going to have to expend energy to maintain any kind of orbit at all. The first thing you encounter is the accretion disk, a dynamic, flat, swirling structure of gas and dust spiraling toward the event horizon. Dust and gas molecules collide and rub against each other as they spiral inward, and the friction heats them to extraordinary temperatures. In the case of black holes, the gravity and friction are sufficient to blast you with high-energy X-rays and gamma rays. As you get closer, you begin to feel tidal forces. The part of you closer to the black hole feels a stronger gravitational pull than the part farther away. The gravitational gradient grows steeper and steeper. The result is a process called spaghettification. Stephen Hawking described it in A Brief History of Time. A fictional astronaut crossing the event horizon, being stretched like spaghetti. The object is pulled in the direction of the black hole and compressed perpendicular to it, distorted into a long, thin version of its original shape. But here is the strange thing. Spaghettification is not inevitable. It depends on mass. With supermassive black holes, the ones at the centers of galaxies, it is perfectly possible to cross the event horizon with no ill effect at all. The gravitational pull is immense, but the gradient is smooth. The change in gravity across your body is negligible. And black holes do not just stretch, they can also flatten. Stars that get too close to supermassive black holes can be compressed by tidal forces into what astronomers call pancake detonation, a short-lived distortion followed by an explosive release of thermonuclear energy. Squeezed like a tube of toothpaste, flattened like a pancake, or stretched like spaghetti. It depends on how you approach and how massive the black hole is. And this is where things get truly bizarre. Imagine a friend watching you from a distant space station as you fall toward the black hole. From their perspective, something very strange begins to happen. You start to slow down. Not because you are actually slowing, but because the gravity of the black hole is warping space-time itself. Time passes more slowly, closer to the black hole than it does farther away. This is called time dilation. From your friend's point of view, your fall toward the event horizon takes longer and longer. your movements appear to crawl. The radio signals you send back are stretched to longer and longer wavelengths, a process called gravitational redshift, as the photons climb out of the gravitational well, losing energy as they go. Eventually, from the outside, you appear to freeze at the edge of the event horizon, never quite crossing it. But from your own perspective, nothing unusual happens. Time feels normal. You cross the event horizon and keep falling. We experience a tiny version of this effect on Earth. Clocks on airplanes tick at slightly faster rates than clocks on the ground. Astronauts on the International Space Station experience time at a slightly different rate. The effect is real and measurable. Near a black hole, it becomes absolute. Once you cross the event horizon, every direction leads toward the center. There is no outside anymore. Every possible trajectory leads inward. From the perspective of anyone outside, you have ceased to exist, not metaphorically, physically. No information can cross the event horizon in the outward direction, not a single solitary photon. Imagine an astronomer sitting beside an astonishingly sensitive detector that reacts to a single photon of any wavelength emitted from beyond the event horizon. Day after day, year after year, there would be nothing but silence. As far as that detector is concerned, there is simply nothing there, a complete information void. Now, here is something most people do not know. Black holes make sound. In 2003, astronomers discovered that the black hole at the center of the Perseus galaxy cluster was sending out pressure waves that caused ripples in the cluster's hot gas. Those ripples could be translated into a note pitched roughly 57 octaves below middle C, far below anything a human ear could detect. Most of space is a vacuum. Sound cannot travel through it. But a galaxy cluster has enormous amounts of hot gas enveloping hundreds or thousands of galaxies, and that gas provides a medium for sound waves to propagate. In 2022, for NASA's Black Hole Week, a team extracted those sound waves from Chandra X-ray observatory data and resynthesized them into the range of human hearing, scaling them upward by 57 and 58 octaves. The sounds were being played at roughly 144 quadrillion and 288 quadrillion times higher than their original frequency. They also sonified M87 star using data from Chandra, Hubble, and the Atacama Large Millimeter Array. X-rays mapped to the highest tones, optical light to medium tones, radio waves to the lowest. The brightest part of the image, where the 6.5 billion solar mass black hole sits, corresponds to the loudest portion. Black holes are not silent, they are just speaking in a language we had to learn how to translate. Everything we have talked about so far involves black holes we can see or detect. But in late 2022, something happened that no one expected. The James Webb Space Telescope began science operations, and almost immediately, it saw things that should not have been there. The first images looked normal. Dazzling blue bursts of light, glowing trails of stardust, curtains of gas backlit by the birth of stars. But then, very quickly, almost every new image showed mysterious, tiny red points. Extremely compact, very bright, distinctly red, and there were so many of them. Everywhere the telescope looked, it found at least one. Scientists began calling them little red dots. The dots were dated to roughly 600 million years after the Big Bang. They appeared in large numbers around that time, then mostly disappeared by about 1.5 billion years after the Big Bang. They existed during a very specific window of cosmic time, and then they were gone. The redness was important. The dots are red for at least two reasons. Their light has been stretched by the expanding universe over billions of years, a process known as redshift. But they are also inherently red, likely full of dust that blocks other wavelengths. Dale Kachevsky of Colby College, who led one of the largest surveys of little red dots, described the situation plainly. The team is confounded by this new population. There are no analogues at lower redshifts. That is why they were never seen before Webb. At first, astronomers thought the dots might be compact galaxies packed with stars, but the density required was impossible. Then they considered small galaxies anchored by active black holes. Roughly 70% of the dots showed evidence of gas rapidly orbiting at about 2 million miles per hour, a sign of an accretion disk around a supermassive black hole. But the dots show no X-ray emission, which is a common calling card of active black holes. And the black holes would need to be enormous relative to their tiny host galaxies. Neither explanation worked. Some researchers suggested cosmology itself was broken, but research now supports the argument that much of the light is from accreting black holes, not stars. Fewer stars means smaller, lighter galaxies that existing theories can account for. But there was a detail buried in the spectra that nobody could explain. The little red dots showed a strong dip in the light they emit below a certain wavelength. The energy it takes to kick an electron out of a specific orbital in a hydrogen atom. This signature usually means a galaxy is full of young, hot stars. But these objects are too small and too young to contain that many stars. Packing them in would be equivalent to squeezing several 100,000 suns between here and the next nearest star system. And then a completely unexpected answer arrived. In September 2025, an international team of astronomers published a paper suggesting that the little red dots might not be galaxies at all. They might be an entirely new class of cosmic object. They called them black hole stars. Imagine a gigantic sphere of hot gas, so dense it looks like the atmosphere of a star. But instead of nuclear fusion powering it from the core, a supermassive black hole sits at the center, rapidly pulling in matter, converting it into energy, and giving off light. Not a galaxy full of stars, one enormous object. The concept of a quasi-star, a black hole embedded inside a stellar envelope, had been predicted about 20 years earlier, but no one had ever observed one. The team had been studying spectral data from the Webb telescope, examining roughly 4,500 distant galaxies over nearly 60 hours of observation time. In July 2024, they spotted one object with a spectrum so extreme it forced them back to the drawing board. They nicknamed it the Cliff. Its light had taken roughly 11.9 billion years to reach Earth. The analysis indicated it was a supermassive black hole cocooned in a fiery ball of hydrogen gas. Joel Leger, a professor of astrophysics at Penn State, said the team had thought they were looking at a tiny galaxy full of many separate cold stars, but it was actually, effectively, one gigantic, very cold star. The gas surrounding the black hole was dominated by much lower temperatures than the millions of degrees typically associated with active black holes. It resembled the atmospheres of low-mass stars based on the wavelengths of light it was giving off. Rohan Naidu, an astrophysicist at MIT, described this as by far the most exciting thing to come out of the Webb telescope. It is very rare in astronomy, he said, to come across an entirely new class of object. He was fully working on this question and setting everything else aside. If the little red dots are black hole stars, they could be supermassive black holes in their infancy. Turbocharged mass builders that eventually shed their gas envelopes and become the bare, roaring engines at the hearts of modern galaxies. As one theorist put it, they become supermassive black holes, and there is one per modern galaxy, so you need a lot of them. And there are indeed a lot of little red dots. Not everyone is convinced. Anna de Graaf of the Max Planck Institute acknowledged that if you asked a random astronomer, they probably would not say every little red dot is a black hole star, but she added that her team was confident. And then, as if the story was not strange enough, another discovery added an entirely new dimension. While examining images from the Cosmos Webb survey in the Webb telescope's archives, Pieter van Dokkum of Yale University and Gabriel Brammer of the University of Copenhagen found an unusual object. Two very compact red nuclei, each surrounded by a ring of stars, giving it the shape of the infinity symbol. They nicknamed it the Infinity Galaxy. It lies roughly 8 billion light-years from Earth. The team believes it formed from the head-on collision of two disk galaxies. But the unusual part was not the shape, it was what they found in the middle. Using data from the Chandra X-ray Observatory, the Very Large Array, and spectra from the Keck Observatory in Hawaii, the team detected a supermassive black hole sitting between the two galactic nuclei, embedded in a vast cloud of ionized gas. A black hole weighing about 1 million times the mass of the Sun, but it was not inside either galaxy. It was in between them. Supermassive black holes are almost always found at the centers of galaxies. Finding one floating between two colliding galaxies, wrapped in a cloud of hydrogen stripped of its electrons, is highly unusual. The team considered other explanations: a runaway black hole, a third unseen galaxy. But either scenario would mean the black hole's velocity should differ from the surrounding gas. So they measured both. They applied for and received director's discretionary time on the Webb telescope to compare the velocity of the black hole with the velocity of the gas. The velocities matched, exactly as expected if the black hole had formed there. Van Dokkum described it simply: they think they are witnessing the birth of a supermassive black hole, something that has never been seen before. And, as an unexpected bonus, both galaxy nuclei also contain active supermassive black holes. 3 confirmed active black holes in a single system. This brings us to one of the deepest questions in astrophysics. How do supermassive black holes form? There are 2 theories. The light seeds theory says small black holes form from collapsing stars, then merge over time. The problem is time. The Webb telescope has found incredibly massive black holes incredibly early in the universe, possibly too early for mergers to explain. The heavy seeds theory says a much larger black hole, up to 1 million solar masses, forms directly from the collapse of a massive gas cloud. One step, no mergers, no stellar progenitor. The problem is that gas clouds do not usually form black holes. They form stars. As a cloud collapses, it fragments and ignites. You need to prevent star formation entirely, and no one was sure that could reliably happen. The Infinity Galaxy may have shown how. During the collision, the gas between the two galaxies was shocked and compressed to extraordinary densities. That compression may have been enough to form a dense knot that collapsed directly into a black hole, skipping stars entirely. Priyamvada Natarajan, a Yale astrophysicist and co-author of the study, had previously reported evidence for a direct collapse black hole in a galaxy called UHZ-1, observed when the universe was merely 470 million years old. But the Infinity Galaxy's black hole formed over 5 billion years after the Big Bang. What excited Natarajan was the implication: nature likely makes black holes via direct collapse throughout cosmic time, not just in the earliest epochs. The team cannot say definitively that they have found a direct collapse black hole, but the data strengthens the case. The velocities match. The ionized gas is in the right place. The X-ray and radio signatures confirm active growth, and 3 separate black holes in one system provide a picture of formation caught in action. Meanwhile, other researchers have been asking a different question. Not what the little red dots are, but where they came from. Fabio Pacucci and Abraham Loeb at Harvard proposed an explanation rooted in dark matter, the invisible scaffolding around which galaxies form. Dark matter halos spin at different rates, some fast, some very slowly. Pacucci and Loeb showed that the little red dots could have formed in halos that sit in the lowest 1% of the spin distribution. 99% of all dark matter halos spin faster. Think of a carnival swings ride. The faster it spins, the further the swings stretch outward. A slow spin keeps everything tight and compact. That is what a low-spin halo does to the galaxy forming inside it. This explains why the dots are compact, why they are rare, representing about 1% of typical galaxies, and why they disappear after about 1 billion years. As the universe evolves, halos grow and gain more angular momentum. Low-spin conditions become harder and harder to produce. As Loeb put it, if you assume the little red dots formed in the first percentile of the spin distribution, you explain all of their observational properties. So where does that leave us? We have mapped the magnetic fields spiraling at the edge of our galaxy's central black hole. We have discovered those fields look almost identical to the ones around a black hole 1,000 times more massive. We have heard black holes sing in frequencies that sat below human hearing for billions of years. We have seen hundreds of mysterious red points in the earliest images of the universe, objects that appear for a brief window of cosmic time and then vanish. Some may be compact galaxies with oversized black holes. Some may be an entirely new class of object. Some may have formed inside the slowest spinning dark matter halos in the cosmos. And we may have witnessed the birth of a supermassive black hole, born not from a dying star, but from the violent collision of two galaxies. A direct collapse of gas into something that, by all our theories, should have been almost impossible. But once matter falls past the event horizon into the black hole itself, we do not yet know what happens. That remains a mystery. The Next Generation EHT project is planning to bring new radio dishes online and increase sensitivity across the array. The goal is real-time movies of supermassive black holes on event horizon scales, resolving dynamics that have never been seen before. A mission concept called the Black Hole Explorer would extend the EHT into space, producing the sharpest images in the history of astronomy. It aims to detect the photon ring, a sharp feature formed by light bent multiple times around the black hole. The properties of that ring encode mass and spin, revealing how these objects grow. Meanwhile, Webb keeps finding little red dots. 3 were found just 1 billion light-years away. Astronomers have detected one in radio wavelengths. Others are searching existing datasets. In one unusual case, gravitational lensing magnified a little red dot's light 4 separate times, providing snapshots across roughly 130 years. And there is a deeper question still. Astronomers are not sure what powered the cosmic dawn, the moment when the first ultraviolet light recharged the neutral gas pervading the young universe. Did that light come from stars? Or from black holes superheating gas? The discovery of dust-obscured black holes hiding in the little red dots suggests black holes may have played a bigger role than anyone thought. We just could not see them until now. As Anna Christina Eilers of MIT said, there is no consensus yet, and even where theories look promising, 1 million open questions remain. Here is what we know so far. A black hole is not an object. It is a boundary, a place where the universe stops behaving according to the rules we have written. Time bends, space curves. Matter is stretched and compressed and swallowed whole. And beyond the event horizon, there is a silence so complete that no detector ever built will hear a thing from the other side. We cannot go there. We cannot look inside. Every instrument we have built, every telescope we have aimed, every equation we have solved brings us only to the edge. And yet, in just the last few years, we have seen things no one thought possible. We have photographed the shadow of a black hole. We have traced its magnetic fingerprint. We have heard its voice. We have watched galaxies collide and witnessed what may be the moment a new black hole was born. We have found objects in the early universe that defy every model we had, objects that may be the baby pictures of the supermassive black holes that now anchor every galaxy we can see. Every answer brings another question, and that is how science moves forward. The universe is much weirder than we can imagine, and all we can do is follow its clues. There are still big surprises out there for us.